Again, we're going to be studying Kirchhoff's circuit laws, which is made up of two: the current law, Kirchhoff's current law, which states that the sum of the voltage going into a node will equal zero, and Kirchhoff's voltage law, which is the sum of the voltages within a loop will equal zero as well. These are good checks for the undergraduate student doing circuit analysis 1 and 2, and I guarantee you'll be wanting to use the Kirchhoff voltage law to check your answers. Okay, now for our 107, we're going to do the introduction to the branch current method. Here we're actually solving the equation using our Kirchhoff's circuit laws. The branch current method is a tool in circuit analysis involving the assigning a current to each branch of a circuit, then using Kirchhoff's current law at nodes and Kirchhoff's voltage law around loops to create a system of equations that can be solved to determine the current values flowing through each branch of the circuit. Essentially, it is a method of analyzing a circuit by considering the current flowing through each individual path within a circuit. So as we see the Kirchhoff's current law, the first law states that the current flowing into a node or junction must be equal to the current flowing out of the junction. Here is our junction. So I1 is going into the junction, and I2 and I3 are flowing out. So the sum of these will equal zero. So I1 equals the sum of I2, I3, and then if you subtract them from each other, you'll get zero. The diagram illustrates how the currents I2, I3 all merge at the node created by the connection of the three resistors, as you can see. Reviewing from lesson 106, the previous lesson, applying Kirchhoff's first law, the current law, we obtain the following equation: I1 minus I2 minus I3 equals zero. This is important. The polarity of the current is determined by the direction of the flow. Currents I2 and I3 are flowing from the node and become negatively polarized, while I1 flows into the node and becomes positively polarized or charged. Applying the second law to the closed circuit loop 1 and substituting for values using Ohm's law gives the following. I'll show you how we got that. Here's our loop. We're assuming current flowing counterclockwise in both loops. You just assume this. Here, I assumed this because I like treating my current as flowing from the positive pole to the negative pole. And voltage drops across the resistor are a negative. So as we come in, we go through VDC plus R1 times I1. It comes out as a negative, though, so it'd be a negative R1 times I1. This comes through here. This is a negative, so this becomes a this is negative. This becomes positive. This becomes negative, so it's a negative R2 times I2 and plus VDC1, and that will equal zero. And that is what we have here for our first equation. Negative R2 I2 plus VDC1 minus R1 I1 equals zero. So that gives us two equations. We need one more because we have three unknowns. So let's go to loop 2. Loop 2, clockwise rotation. These currents having two voltages here kind of mess us up. So this is negative to positive now. So there'll be a positive R2 times I2 is the voltage drop across this resistor using Ohm's law. This coming into here, this is positive. So this is a positive. This makes this a negative R3 times I2 or I3, R3 times I3 right here, minus a VDC2 coming into here, positive, negative, minus VDC1. So that equation becomes negative R3I3 minus VDC1 minus VDC2 plus R2I2. And again, this is negative. This comes out positive. Negative to positive be plus R2I2. Coming through here, we have loop 2. Coming into here, this is positive and negative. That makes that a negative R3I3. Going through VDC2 makes that a negative. VDC2 coming through VDC1 makes that a negative 1. The sum of all these voltage drops equals 0, as it is expressed in this equation here for the second loop, closed circuit loop 2. This gives excuse me. This creates a system of linear equations, I1, I2, I3, which enables us to solve for our three unknowns. As you'll notice in the second equation, loop 1, I3 is 0, and in the third equation, loop 2, I1 is 0. So here we just go over again a review of how we created the equations. Let's go ahead and solve the equations by assuming the following values for the lump components. R1 equals 100 ohms, R2 equals 200 ohms, R3 equals 300 ohms. VDC1 is 3 volts and VDC2 is 4 volts. First, we must solve I1 in terms of I3, I2. So that's simple. You just bring I3 plus I2 to the right of the equator, the equate sign. Excuse me. Using equation 2, substitutes this in for I1, making the reduced equation 1. So substituting this right here for I1 reduces to 200, negative 200 I2 plus 3 volts minus 100 I3 plus minus 100 I2 and negative 100 I2. Reducing further creates this equation. We multiply both sides by a negative 1 to just make it positive. You're allowed to do that. It's an algebraic trick. Anything you multiply on the left side of an equation, if you do it on the right side of the equation, it does not change the equation at all. And you can use that method to help you solve for different types of equations. All right, so that leaves us this right here. So now solving for I2, we have 3 minus 100 I3. We bring this over to here, divided by 300. So we bring the 300 from I2, divide that into 3 volts minus 100 I3, and that leaves I2 with this value right here. I2 equals 0.01 plus a negative 0.3333. Be sure you keep your signs and don't drop a sign. That's why I still, even though I'm adding, I could have put a subtraction sign here, because we're adding a negative number to this, but this helps me keep my sign, and I know that I have the correct equation. So now we substitute I2 into equation 3 for I2. We know what I2 is because of this right here, thus giving us a new equation with only one unknown. That one unknown will be I3. So here's I2. We substitute this in for I2, giving us a negative 300 I3 plus negative 3 volts DC minus a negative 4 volts DC. Remember, we're not dropping our signs because we don't want to miss any, times 200 R2 times I2, which is 0.01 minus 0.3333 I3. That reduces to this equation here, which is 200 times 0.01 minus 0.3333 times I1 plus a negative 300 I3. Remember, we don't want to drop our sign. That's right here. equals 7 volts DC. Reducing further down, we have 2 minus 66.6 I3 plus 300 I3 equals 7. Bringing a 2 over to here, that reduces that to 5. Adding these two together makes a negative 366.6 I3. Now solving for I3, we just bring this under the 7 or under 5. 7 minus 2 is 5, and then divide, keeping the sign for I3 here. So That's I3. Now we have two unknowns. We know them, I2, I3, and we want to know I1. We go back to our first equation, which was I1 equals I3 plus I2. We put those into here. Remember, when we solved for I2, it became 0.145453. This is very important that I didn't drop this sign because that changes this to a positive, and that gives us this amperage here. So I1 equals I3, which is right here, at negative 0.013636, 0.0136. I just kept it to 4 significant digits. I2 is 0.014545, and I got those truncated. But it equals 0.0009, and let's see, 14545. I gotta change that. 145. Oh, I rounded it up, is what happened, because it is a positive, and I rounded it up because it is a 5 or greater. That leaves us I1 equals 0.00090009 amps, which is equivalent to 0.9 milliamps. Now I want to test my accuracy. I want to see if I got the correct values. So I go back to Kirchhoff's current law, which is I1 minus I2 equals I3 equals 0. I put I1 in there, which is 9 milliamps, minus I2, which is negative 0.0136. Well, that's I3. I2 is 0.014554. But when you add these together, it equals I1 equals 0.009 amp. So I bring that down to here, and that equals 0. Stop. Now it's time, since we got our solution, to do the QUCS simulation and see how close we are with that and compare our results. It's going to be fun. All right. We're now going to build the circuit that we've been studying with the QUCS simulator. So go to your icon on your desktop, open up QUCS, start a new project, Kirchhoff's circuit law, create. Let's get a document setting. We want the grid to be 5. Apply. The frame, want an A5. Select whichever you want. Title. Drawn by your name. The date. Hope everybody had a good Christmas. Version 1, apply, say OK. All right, now we have our schematic. So we need to get our lumped components first, which is 3 resistors. There's R1, R2, R3. We need power supply and a ground. We'll bring the ground over here. And since we had to have a ground to do our DC simulation, we also need a very large resistor, which won't actually be in the solution, but it is to just allow the spice generator to do the proper calculations. More on that later. Okay, now we need a power supply source. DC, this would be VDC1. Wow, what happened there? This locks up just for no apparent reason a lot of times. Delete that. Oh, I did not disable, so I should have hit escape after I selected that. Okay, we need another power supply. VDC2, and this will be there we go. VDC1, we want the polarity. I have to rotate it to make it look like the schematic. All right. This needs to rotate 180 more degrees. Rotate twice. All right. We need our other resistor for the biasing. This is going to be such a large resistor that very little current will go through here, which will give us a small error. Okay. Now we know that R1 is 100 ohms. Apply. R2 is 200 ohms. Apply. R3 is 300 ohms. Apply. R4 is going to be 10 meg. Ten meg ohms. Let's see if it takes that. It did. All right. So now we'll wire wrap the circuit. Oh, a V1, that needs to be our V1 DC. We applied it to be, hang on, 3 volts. Apply. Okay. And V2 is 4 volts. Now, I've discovered a little trick using the cursor keys and zooming in that really increases the ease at which to do your wire wrapping or your circuit connection. So just zoom in. We'll do R4 first. If you zoom in, disable that. We want to connect the red circle over the other red circle. Once you do that, you get your black dot and the circuit has been connected. Then you can zoom back out. It makes it real easy to connect all this together. So I'm not going to go through that step by step. But other things we need to add is the simulation. We need to add the DC simulation. Disable that. And then we need our table, our diagrams. And we want a tabular table. We'll bring that down to here and put that right there. But since we're not ready for it, we'll cancel that. And then, so I'm going to break off from here and bring up the completed circuit. The probes you see in the completed circuit are current probes, and so you need to make them in series with the current so that they'll measure. As you can see from the table, all our results are exactly what we calculated. I1 equals 0.9 milliamps, I2 is 0.01454 amps, and I3 is 0.013636 amps. So our math equals the simulation. Excellent. Okay, that's it. Please don't forget to click like if you enjoyed the video and subscribe for new videos.